I'm looking at just this point is equal to 0. At that point, the incident plus the reflected waveform is equal to the transmitted waveform. So these are voltages, KVL. And if we look at the Kirchhoff's current law at that point and look at the currents, so this will be the current coming in. So this is I0, this is the current I incident going in this direction, plus the, So remember that what do I want to hear right here? Plus, minus VR0 plus negative VR0, VR minus z equal to 0. Sorry, it shouldn't have pluses and minuses. Here, no, that's good. Minuses here. Over z equal to 0, 1. So this is the current going in the opposite direction. Is equal to the current going into the load. So you'll have a current going into the load here, plus a current going in that direction. So a current going to the load plus Vt plus z equal to 0 over Z02. That's a transmitted current. So I'm setting up two equations just for this point where everything comes together. The voltages have to equal to each other, and the currents also. This is sort of some of the voltages around this KVL have to be equal to each other, and so do the currents. Okay, so we know the relationship between this is the reflected wave and this is the incident wave. So the relationship between those two guys are defined by this reflection coefficient. Okay? So I can basically substitute that using the reflection coefficient. So the relationship between the reflected wave at z equal to 0 and the incident wave at z equal to 0 is the reflection coefficient at the load, and that's equal to load minus Z01 over Z load plus Z01. Actually, this is Z load parallel. Z load parallel. Z load parallel. Okay. So what's the difference here? So when you're looking at when there's this guy's hanging off this end, this impedance changes, right? If this guy wasn't here, imagine if this guy wasn't here, my reflection would only be because of this guy, okay? When this other transmission line is hanging off of this endpoint too, it looks like I have this impedance in parallel with this impedance. So when I'm looking at the reflection, I have to consider that both of these guys look like a load at this point for the reflection. Okay? Any questions about that, guys? But he looks a little phased out now. Good? So, yeah, Jasmine.
Can you go over what VI, VR, VT is?
Sure. So this is we started off by saying we've got a transmission line that's a semi, you guys remember the semi-infinite transmission line? So basically the load is, the source is somewhere back here. It launched a waveform in here. And basically VI is what we were calling V0 plus before. Okay, so it's the incident wave that got launched from far away. It's coming towards this load. Okay, VR is what got reflected from this load point. Okay, except we also have another transmission line hanging there. Okay, so it's not just the load, it's the load in parallel with the transmission line as far as the reflection is concerned. You guys with me? So it would be the difference as if we had a simple, it's as if I said, okay, do a voltage divider here, and I have, this case, oops. I have this case, right, in a simple voltage divider. And now I'm saying, well, I'm going to add another resistor here, which is another transmission line. That's going to affect, the voltage here. It's going to affect the impedance looking into this point here, whether this guy's here or not. And this guy, this is like a sort of a lumped version of what we're doing here. We're saying initially we just had this guy as the load. When we put the second transmission line here, it's going to be in parallel with this. So as far as when you have to include that in your thinking about what gets reflected back. Okay? Everybody good with that? Claire, you good with that? Okay, sorry. Yeah.
Is VR when being reflected, does it have the same phase as the V incident?
Does it have the same phase? You would have to add them to know. It's not going to have the same phase, no. Not necessarily.
Because I was just curious to know the KVL that we did.
Yeah.
I'm supposed to have the incident minus VR, but I guess if it's not in the same phase, adding will still give us the difference. So going back to the same.
Yeah, to add, I think we're looking just at this point, z equal to 0. So that's what I'm doing the calculations to make it easier. Otherwise, you would have to include e to the minus j beta z, or e to the either plus or e to the minus j beta z. Right, and then remember, depending on the waveforms, we were assuming we are launching a sine or cosine wave in there from the voltage source with a z component in there. So the whole point of calling this endpoint z equal to 0 is make life easy for us when we're doing the analysis at z equal to 0. So I'm like plugging in z equal to 0 for all these things. Otherwise, I would have to keep track of all these phases and all that stuff. Does that make sense for you guys? No. Yeah? So, I mean, V0 could be really anything coming in. And V0 minus would just be the reflection coefficient times that anything. Yeah? Okay. So this is what the reflection coefficient when you put the transmission line looks like here, and this parallel ZL parallel is just a parallel combination of the load impedance and the impedance of the second transmission line. Okay, so I'm gonna leave the working out the details of basically solving these. Basically, you can use these two equations to solve between the ratio of the transmitted wave, VT plus at z equal to 0 over V in plus and z equal to 0. This is called the transmission coefficient. It's called tau, and it comes out to 2ZL11 over ZL11 plus Z01. Yeah.
Maybe because I gave in later, what does that, what does the ZL with the double stroke mean?
The ZL double struck means that Z load parallel. It means that if just ZL by itself would be as if this, there is no load here, so it would just be ZL. As soon as you plug this second transmission line, this load impedance isn't just ZL, the load that you thought you put in, but it's that plus this extra transmission line. So ZL11 is those two in parallel. Okay, sure. So, sorry, because we're still writing.
Is that a 2 next to the coefficient? So you multiply that by 2?
Here?
Yeah.
Yeah,
That's 2.
yeah. I was just working out the details of this. Yeah. Okay, so if I was going to give you guys a recommendation, is that just remember the reflection coefficient of a transmission line equation for the rest of your life. Okay, so that's ZL minus Z0 over ZL plus Z0. Remember that. You're going to use that probably for the rest of your life. Transmission coefficient, I don't really remember it. To me, it's a special case. You may end up somewhere where you use it over and over again, but to me, this is a special case. I think it's interesting from the standpoint of how, looking at transmission lines and seeing, how you get reflections and transmissions, but it's not something that I'd say you guys should stress over, this transmission, the transmission coefficient. Okay? Everybody good? Okay. All right. So that completed what happens at the load. So the load, it's either just sitting there by itself, and or there's another transmission line connected to it, and you either just get a reflection, you get the signal fully absorbed at the load, depending on the load impedance, or a combination thereof. If you have another transmission line connected, you might get something going into that. Maybe I should give you guys the window analogy again, right? So when you look at a window, the light's hitting the window, okay? And depending on how well the window's coated, you might get some reflection off the window to you, right? So that's the difference between, if you can think of it as the impedance of the air is different than the impedance of the window, right? So you can kind of see some reflection at the window, but then some of the light goes through and hits the other person on the other side of the window, and you can still see them, okay? So that's the case where you get a partial reflection at the window and a partial transmission. Because the fact that you're seeing somebody on the other side of the window means the light went through and you can see them, right? Like a mirror will have full reflection. There's nothing, you can't see the wall behind the mirror. I guess it's just a way to think about those things in some ways. Okay, so anyway, so those are that what happens at the end. So is it Darren? Darian, thank you, Darian. So Darian was asking about this how we look at why do we have a characteristic impedance and a load impedance, and we talked about that's how we're breaking the problem down to help us analyze this complex situation. So now what's left is going back to the source that we keep kind of saying, well, the source is sitting at minus infinity. Now we're going to look at the source because its impedance also affects what gets launched into the transmission line. Okay, so all of this stuff is something launches this V0 plus in, it hits this point and does something, reflects, transmits, but how does that get generated? So how does this thing gets launched? And that's what we're going to talk about next. Okay, that's called, so that is going to lead to worrying about something called input impedance. And that's typical nomenclature as Z sub S. Okay, so so again, Z0 is the characteristic impedance of the line. And that's given by the L and the C of the line. So that's Z0, Z sub L, is the load impedance. And that gives the reflection coefficient. Combination of that and the characteristic impedance give the reflection coefficient at the end of the line. And Z sub S is going to tell us how we generate V0 plus. And that's, this guy is the waveform actually launched into the transmission line. Okay, so that's the amplitude of the voltage going in the positive Z direction. Okay? All right, so I'm going to make to look at that, I'm going to do some simplifying assumptions. Okay, then we're going to look at if they're valid or not, or what do they mean. Okay, so for one thing is, so now before I get started, so we say we have this transmission line of length. Now we're going to call this, instead of a semi-infinite transmission line, we're going to say it has a length L. So we have a source sitting at minus L, and this we're going to call Z equal to 0 is where the load is sitting. Okay, so this is source is sitting at minus L instead of at minus infinity. So the first assumption, so assumptions. So one is that source does not have internal resistance. Does not have internal resistance. This means that Z sub S is equal to 0. if I draw where Z sub S would be, it would be here. And it can produce a pure sinusoid. What does that mean? That means we can assume a single frequency f for the waveform coming in, or omega. So we don't have to worry about keep track of multiple frequencies. Okay, that's what the pure sinusoid means. Second assumption is that transmission line is lossless. We've been dealing with that so far, which means it only has inductance and capacitive components. 3 is that we have a oscilloscope at load end, meaning that we're going to assume that the load impedance is approximately infinite. It's very high. So this is the same as saying the impedance is very high, or that it's an open circuit. And that means that the reflection coefficient is +1 and V0 minus is equal to V0 plus. Let me just remind, I'm going to write this here so you guys can keep remembering these things that are important. Although I know I put Jasmine a sheet with the important equations as we go. But remember, reflection coefficient is Z load minus Z, the characteristic impedance, over Z load plus the characteristic impedance. And then there's a few cases, just to remember. You just plug in the numbers, right? There's the open circuit case, which means Z sub L is about infinity. That means the reflection coefficient ends up being +1 if you just plug it in. There's a short circuit case where Z sub L is equal to 0, and the reflection coefficient ends up being -1. And then you have the case where, let's say we call it matched impedance, which means Z sub L is equal to Z sub 0, in which case the reflection coefficient is 0. So those are worth just remembering. Okay? And in a typical case, your typical transmission lines have characteristic impedance, or so it won't go wrong if you assume in a typical case. So typical, I'll call it typical microelectronics case. How's that? So that way I won't get into too much trouble. The characteristic impedances in typical cases they are kind of in the 50 ohm to 150 ohm range, depending on L's and C's that you can get. And then think of a oscilloscope. So it's Z sub L. Its input impedance is pretty typically 1 mega ohm, or it might have a 50 ohm input. So a 1 mega ohm, so a resistance of 1 million ohms is pretty close to being infinite compared to 50 ohms. It's much, much, much larger. So it looks like an open circuit. If you have a 50 ohm transmission line cable going to an oscilloscope, it's gonna look like, the oscilloscope's gonna look like an open circuit, and it's gonna basically reflect that all that way back. Okay, so that's what this assumption is for our analysis. So we're saying we're looking at the end of this with the oscilloscope, and that's why we're calling it infinite, because it's much, much higher than your typical transmission line. Okay, and then so imagine if you're sitting in the lab, you have a voltage source, and in the voltage source, so this would be the voltage source here. Okay, and that voltage source you're gonna put in. I'm assuming you guys have used voltage sources. You put in like sine output, sine wave output. You put a certain frequency and whatnot. You're making the assumption that it's outputting a pure sine wave. There's no such thing as pure sine wave in real life. There's always distortions to the nth level, but a lot of times you can assume a voltage source will give you a clean sine wave coming out at a single frequency. Typically they have voltage sources, or not typically, all voltage sources have some kind of output resistance. Usually it's 50 ohms. In this case, we're assuming it's 0. So it just has 0 resistance driving the output line. Then we're assuming you're using that voltage source to drive a transmission line. You can assume that's a cable. Think about that being a meter long, and it goes into your scope, which has effectively an infinite input impedance. Okay, so if we now let's look at what that means. Okay, so another thing I wanted to write down is this one. I don't think it's important to memorize it, but I'm just writing it down because we derived it last time, and I'm just going to use it as is. If you have a case where you have a semi-infinite transmission line with impedance Z0, and you have an open circuit, or Z sub L is equal to infinite. We came up with what would be the total voltage last time as a function of Z is equal to 2V0 plus cos beta Z. And the way we did that is we said V0 is whatever it is coming here. The reflection coefficient is +1. The wave going back is that reflection coefficient times V0 plus, and we added those things, and we included the phases in our addition, and we ended up with this being the equation for that. So I'm just going to use that from last time. So this is the voltage that you would see on a lossless transmission line that has an open circuit and load, and it includes both the reflection and the forward going and the reverse going waves. That's why we end up with this 2V0 plus cos beta Z. Okay? And we assume that the input, sort of the V0 plus was, is V0 plus cos beta Z. That was the input. So basically the total voltage is sort of a double version of that. Okay? Because of that particular reflection coefficient. So I'm just going to use that as is without redriving it, so that we're going to end up with V sub Z. So the phasor equation for that is 2V0 plus cos of beta Z. Okay, so now I want to look at what this voltage is, this equation gives me at this point, right? So this voltage is, our transmission line goes from 0 to minus L, or minus L to 0, whichever way you're going to look at that. So let's look at what happens in this case here. Okay, so V hat of Z at Z is equal to minus L. So this is the voltage at the source end. Is equal to 2V0 plus cos of beta L. So I just plugged in minus L for Z in my equation. So this is the voltage at that end. Cosine is what's called an even function. That means that this is the same as 2V0 plus cos of beta L. So for cosine, whether you have a cosine of minus something and cosine of plus something, it's the same thing. Okay, so I'm going to get rid of that. So that by KVL is equal to the source voltage. So this voltage here is the same as the source voltage if Z sub S is equal to 0. Right, it would have to be. You guys with me? So this is by KVL. Okay, so basically this all gives us V sub 0 plus is equal to Vs, whoops, put the hat in the wrong place. Vs hat over 2 cos beta L. Yeah.
So this is only if Z sub S is 0?
Then I can do a KVL at that point. Otherwise, I would have to include, only if V sub S is equal to 0 do I just have these two components for KVL. If Z sub S was not 0, there'd be a voltage across V sub S, and I would have to include that in my KVL, which makes life a little complicated. You guys with me? Need to copy this stuff down? Slow down? Keep going? How is the pace? Okay? Too slow? Speed up? Yeah.
So, can you please repeat what you just said? I didn't hear it.
So so I'm saying that we previously, when we looked at, so if you don't look at this, we figured if you launched a voltage into this thing, we figured out what the voltage would be because of the voltage coming in, the voltage going out, if this guy is infinite. And that ended up being defined by this equation, okay? So basically I'm saying if Z sub S is 0, okay, I can do a Kirchhoff's voltage law here and say that the value of this equation at minus, when Z is minus L at this point, has to equal to what the voltage source is putting out. Right? So I'm just saying, hey, if the voltage source is hanging off of that node and the line equation says that's the voltage of that node, they have to equal to each other. Okay? So does that answer your question? So just making really simple statements. So now basically what it's saying is, this equation says the amplitude of the voltage launched. So imagine if you have this situation with infinite, let me redraw it again. So, because it's very specific. The specific case we're talking about is we have a voltage source. We have a voltage source that has no resistance. It's zero resistance output. Not a realistic scenario, but usually they're low resistance. Okay, voltage sources in the lab, if you look at them, they're like probably 50 ohmish or maybe 5 ohm, depending on what you get. They try to make it low resistance sources. Okay, if that's driving a transmission line of length L that is terminated with an open circuit at its end. If this is the situation you're doing, so that's the calculation, or V0 plus is V sub S over 2 cos beta L. So this means that the voltage that I'm launching into this guy, that's going into this direction, the amplitude of that is whatever my voltage source is pumping out over 2 cos beta L. Okay? So a very, very simplified case. In a general case, this will have a source resistance, and in a general case, you might have any kind of a load impedance here. So in this very specialized case, this is the voltage value that I'm like outputting into the transmission line. Okay? But maybe a more important thing is the analysis methodology. Okay? Notice how we've got these, generally, we have these 3 components in a transmission line system. This is very general. We have a source that's launching stuff into the transmission line, and that source has some amplitude and some impedance. We have the transmission line itself, which has some characteristic impedance and some length. And then we have the load that has some load impedance. So this is sort of a very general case. And so we're seeing how you would analyze it. Again, going back to Darian's question, this is a methodology for analyzing potentially a pretty complicated situation. We're looking at it, we broke the problem down into these 3 different things, and then we figured out what sort of this does, and then what this does, and now we're looking at the combination of what this does in a very special case. Remember, this is a very special case. Okay, what I'm telling you right now. Okay? Any questions about that? So now we've ostensibly covered all the 3 components in a transmission line. So you guys already know everything there is to know about transmission lines. Just kidding. Okay. Okay, so now I'm going to tell you guys that what we just did has some holes in it in terms of the source, because we're going to have some serious problems here if you don't think about reality. To do this simplified calculation, and sort of as a next thing, we're going to do a more complicated version of the source impedance. But I wanted to start here where you guys kind of see what we're doing as a methodology. But if we just take this as it is, in some cases it's going to give us a nonsensical result. Okay? Because we have this thing down here. Look at when cos of beta L, so remember that beta is 2 pi over lambda. Lambda is the frequency of the waveform going in, okay? So when beta L goes to pi over 2, look at what happens here. When beta L goes to pi over 2, the cos turns into 0, okay? And you get an infinite voltage launched into the transmission line, which is like, sounds like you could get, I mean, first of all, you don't have infinite things, right? And second of all, it seems like you can get something from nothing, right? You put in 1 volt as your voltage source, and if you just picture a transmission line length perfectly, bless you, you're going to get infinite voltage here. Sounds like you're getting something for nothing. So I'm going to talk about, well, after we talk about the general case of Z sub S, I'm going to come back to this and say why this is not the case in real life. But it turns out this actually does happen, something close to that. So people discovered, this is called as I found out, I'll talk about this a little bit later. Forgot the name of this. So it's called the Ferranti paradox. So, which goes back to like 1870, when people were first using transmission lines for power distribution. Okay, they noticed, whatever, if this dude Ferranti, or maybe it was the investor for this power distribution, I forgot who it was. People noticed that under certain circumstances, the voltage at the input of this power source was actually higher, at the input of this power transmission line. I think it was 200 kilometers or something, 120 miles, whatnot. The voltage here was higher than what they were inputting in. They noticed that. So something like it happens. It's not crazy, just that you have to make sure, that you put in the right values. So for example, the source resistance is going to be finite. Transmission lines are not lossless. There are resistive components and all that stuff. But something like this does happen. Okay, so let me just tell you guys what this specific case is. So, well, I guess that's, so beta is 2 pi. So if L is lambda over 4, so for a very specific length of transmission line, for the case of an open circuit transmission line, okay, for this case, you get V sub 0 plus gets, let's say, very large. That's true. V0 plus will get very large in that case, not very specific case. Okay, it won't go to infinite, but we'll talk about it later. And this is called, by the way, this is called a quarter wave. This case, if lambda is equal to 4, this is called a quarter wave transformer. This one is a 4. Okay. So I'm going to suggest we take a break here because half of you guys look like you're about to pass out. And we're about to hit the analysis of what happens when the impedance of the source is not 0. And that's a little bit more complicated, so I think you need a breather. So how are you guys doing so far? Did you guys, everybody good with what we covered right now? How are you guys feeling about transmission lines generally? Okay, so I promised to Jasmine and other people, everything that's coming to you guys is coming from Jasmine. The rest of you guys got to ask for stuff. Also some difficult homework problems and like sort of a suggested text. So I finally found something that I like. So I'm going to put that up this weekend. So it's going to be a non-graded homework, right? So the idea was I'm going to give you guys we have the quizzes. We're going to have another one next Friday. Those are not graded. They're in the class. So don't panic if you didn't take them. They're like sort of multiple choice, meant to engage you guys. We're gonna give those at like sort of the halfway point in the class, just to get you guys juices flowing. And the idea behind the homework problems, which you'll also get a solution for, is meatier problems that'll engage you guys more, and hopefully it'll get you more prepped for whatever midterm or tests will come up that will be graded. Okay? So again, I found some stuff that I liked. I'm gonna have those guys of this weekend up for you guys to look at with the solutions and with like some reading ideas. Okay? All right, so let's take a 10-minute break, or 8-minute break. Be back at 9:10.